So, hello everyone. I'm a postdoc at the University of Glasgow in GCC group, and this is my last week at this post as I'm moving to a new post next week in a different in a company actually. And today I would like to share with you what has been done until now with respect to developments in MOFEM and other tools aside MOFEM in order to try to tackle the problem that both Sandy and Sakine presented earlier to characterize piezoelectric materials using finite element technology. And this work has been done with Andrei and Sakine and with the support of Sandy, Chris, and Łukasz. So this is not end game, this is ongoing, and I'm going to show you what has been done and what is needed to be done later on in order to achieve this goal. So I'm going to give you the motivation of our work, the description of the mathematical description of the problem, some verification that has been done for the implementation that are done until now, also dynamic analysis results, and finally the conclusions and the future work. So as far as I understand, the interest of the engineering community towards piezoelectric materials is now at its peak, because there is a need also to change the materials that have traditionally been used, that are lead-based materials. And there are many applications for such materials, as you have already seen in previous presentations. So in order to reduce the consumption of lead-based materials that is negative for the environment, there's new materials are coming into play, which are not well understood. So, you know already, that's why we need to characterize them. So in order to understand better those materials, we thought of producing tools and packages that are not bound to a license, since we have already been doing this for other applications, as you saw from Łukasz's presentation. So while Andrei and I were trying to crack things and put things into contact numerically, we thought that it was a good idea when we had spare time to try and model this in MOFEM. So the main concept of this presentation is that I'm going to show you the theory and the results of the implementations done in order to model piezoelectric materials, and also give a glimpse of what Andrei is going to present later on regarding the tools that are out of MOFEM in order to be able to use Python-based libraries in order to eventually be able to run in an interactive manner MOFEM, and also be able to use it to perform optimization analysis to characterize these materials. So the problem we try to tackle is a coupled problem. In the first row, you can see the second order in time differential equation, first order in space. This is the conservation, of linear momentum. And the second one is the Gauss law. So we try to fulfill both of them simultaneously. And here you can see also these really damping terms that are quite interesting eventually, and we try to understand them, and we are still not really at the position to understand them, but we have added this here in our search for trying to develop the model to at least include this. And here, what you can see is that with U we present the displacements, with phi the potential. Strains are defined as the as the symmetric tensor of the gradient of displacements, and the electric field is the gradient, the negative of the gradient of the potential field. And then Cauchy stresses and electric displacements are presented like this, which is essentially D. Here you can see subscripts. This means that this is formally fourth order tensor, and E is a third order tensor, and epsilon is a second one. But eventually, due to symmetries that arise, if you take this collection of D's and E's and epsilon matrices, eventually you get out the matrix that was presented by Sakine and Sandy before, that is the coupling matrix of the two fields, namely displacements and potential. So it is not something new. And also there is this alpha parameter and beta parameter that are material parameters for damping. And as I said, these other matrices are also material parameters. Sorry, I'd rather like to say that really damping is not really a material parameter, but structural parameter, as Łukasz said earlier. So that's why we are not really sure on how to use them at the moment. So at the moment, these are 13 parameters that we would like ideally to find for the characterization. And in order to solve these equations, we use the finite element formulation. So what we do is that the initial equations we had, we multiply them by variation of functions, and we integrate them, and we try to find the solution for them for any function that will multiply these terms with. So this is formally how the finite element approach is starting. Like, this is the onset of applying the Galerkin approach, the so-called Galerkin approach. And in order to solve this, we need to use discretize the problem as this, where the approximated field is the linear combination of some test functions that we are using to solve this problem, that are shown here as n for the displacements and a capital phi for the potential. And when we do this, once we do this integration, we deal appropriately with some of these terms, and then we discretize the problem. We end up with having a coupled system of equations that take into account the second derivative in time, the first derivative in time, and the actual fields to solve. And we are solving this in time, taking into account some essential boundary conditions. So in order to be able to solve this problem, we need to fix some of these fields in order to make sure that our specimen, our numerical specimen, does not fly away. So of course, we just show again the experiment that we have always in mind in this analysis that I'm going to present. Here there is the apparatus where the specimens are placed, and then an electrode is put on the top of this, and on the bottom there is the grounding. And then this electrode gives a pulse in time, and the changes in the charge in time is measured on this surface. And from this, once we get the time history of these changes, and knowing also the time history of the changes of the potential, we can evaluate the impedance frequency diagram that you can see here. So something similar is happening for the case of the finite elements, where we apply the same boundary conditions, but we want to evaluate on that surface that we apply the voltage pulse, the changes of the charge. And this change is evaluated like this. we take into account the charge on the surface, and we find the time derivative of this. So the charge is essentially the surface integral of the normal projection of the electric displacements, which is evaluated by this expression. And then in order to evaluate the integral, the impedance, once we have evaluated the full time history of these changes, we evaluate the phase diagram of the impedance as the ratio of the Fourier transform of the potential time history over the Fourier transform of the current time history. And this is based on this prescribed potential in time that we set on that upper boundary. So in order to do the optimization, what is the pipeline that we have in mind is that once we have the experiment and its results, we set up a similar situation for the finite element model. We perform the analysis in time. We evaluate the impedance diagram, and then we compare them. And depending on how we choose to compare these two things, we get an objective function, or rather a cost function. And if this comparison meets some criteria, we have to check whether this converges or not. So if it meets this criteria, we will, if it doesn't meet, this criteria, we will update the material parameters and go back, to the finite element analysis with these new parameters, run again, and make the check again, and see again if it converges. And at some point, hopefully it will, and then we have the material parameters that we aimed to find. So because we are using finite elements, as Łukasz said, we are very interested to be able to control the error. So we have tools in our hands that we could potentially use in order to improve our numerical schemes for faster solution and more reliable solutions. And at the same time, we have special basis functions that I showed earlier for the discretization of the problem that behave better than standard basis functions in commercial codes, as they preserve the positive values of mass for higher order of approximation, because usually this is not fulfilled in standard basis functions. And what we would like also to do in the future is to take advantage of such schemes for basis function and do fast integration in order to perform very fast analysis. So to verify the model, we did a verification that is for quasi-static conditions. Here you can see a cantilever that is made of the same material on top and bottom, but there is an opposite gradient of electric field upwards for the upper part and downwards for the lower part. Here you can see the dimensions of the problem, and we compared the results of MOFEM and the analytical results for these given boundary conditions along the whole length of this cantilever, and we found that there was a good match between them. So now for the dynamic analysis, we performed a dynamic analysis using a cube of these dimensions, and we applied a pulse for the prescribed boundary conditions on the top of this numerical specimen that looks like this, and on the bottom it was grounded, so the potential was constantly equal to 0 throughout the analysis. And from that, we took, as I said earlier, the time history of the charge changes on the top of the specimen, and from that we took we performed FFT fast Fourier transform of both charge rate and potential, and we evaluated the impedance for this. And what we ended up with, as we wanted to reproduce the results that were presented in Fen et al. 2020, we ended up having this. This was the best fit that we could manage to do for the current version of the code. So it's not that far, but it's not as good as at the moment is managed to be done by OnScale. So even though the problem is a linear problem, we understand that there are things that we need to understand better on how to manage to reproduce these results. And on the top of this, we realize that we don't really understand what actually really damping does, especially for higher orders, because here you can see that with black color, these are the results from this paper, and everything else are results from MOFEM for various orders of approximation. So we realize that for different orders of approximation, depending on the base that we use, we have a different behavior of the damping parameters. So we need still to do both improve the model in MOFEM, but also understand better the physics behind this. And here you can see the differences for the same order by choosing different basis functions. And this is something, again, that we need to better understand. What are the implications eventually for choosing the base? We know from mathematics already that Bernstein-Bezier base should behave better because they have these properties that I mentioned earlier. So I think we are going to go forward with this base. So to conclude, I showed the current stage of the MOFEM implementation of piezoelectric material modeling. We ended up using the Bernstein-Bezier base due to the qualities that they bring. We understood, as I said earlier, that the damping parameter alpha is a non-objective parameter because it's more a structural rather than a material parameter. And we aim also to do fast integrations that are coming with this base that I mentioned, and also to substitute the relay damping totally by using the imaginary coefficients that were presented before. And this is something that is relatively natural for MOFEM, as it's like a lot of the effort that has been done for the development of its architecture is to be easy to work with many fields. And when we are going into the complex coefficients, we essentially go into complex fields that you can see on the right. And this means that from a two-field multi-physics problems, we go to a four-field multi-physics problems. And this is quite natural for MOFEM. It's not that there is a need of extra work in terms of the parts of the architecture. What is needed to be done, and at some degree it has already been done, is to add these extra equations as extra parts of the already presented model. So that is all, and thank you very much. And this is an open container or you can find online where this model is now available. Thank you very much.